So let's look at recognizing functions from graphs, as well as using our function notation with graphs as well. So in the first video where we introduced functions, we talked about kind of seeing how a graph is not a function if you can see an x value that has multiple y values. A shorter way of describing that is with this vertical line test, which is a way of just taking this test to a graph, and this will show whether or not it's a function. For short, you might see this as VLT for vertical line test. But the idea is if we go to our graph and we draw every possible vertical line that we can, if anywhere on that graph it intersects more than once, then the graph does not define a function. So let's see that in practice. That can be hard to listen to in words and apply. So let's see how this works. So this function here, what I want to do is imagine every possible vertical line that I can draw, and this is going to get messy, but every possible vertical line, I'm not even drawing all of them, just too many of them. But the idea is that with each of these vertical lines, and maybe all of these would intersect in this case, sometimes it doesn't intersect at all, that's totally fine. When it does intersect, it should only occur in one spot. If it crosses more than once, that's showing that for one input, there's multiple outputs. But in this case, we're seeing just one intersection point for each of those cases. So this is a function here. With this case here, if I imagine my vertical lines, like that's good, good, good. Even right here on the y-axis, that line's okay. It looks like it's crossing twice, but because that's an open circle at the top, it's not actually defined there. So technically that's only crossing once. But if I go just a little to the right there, and this one I'll draw on here. If I go a little to the right, what I can see is for like near x equals a half, I have this positive output and negative output, and that can't happen. So this is not a function. For this case here, if I start drawing my vertical lines, cross once, 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 this is a function. And this last one here, and as soon as you can visualize where it fails in one spot, then it fails everywhere. So as soon as I can see a line about there, where I have this output up here and output down there, then it's not a function. So that's our vertical line test for showing from a graph whether or not something's a function. Now, using our function notation with graph, so first thing we can do is determine whether or not we have a function, so whether or not we should even answer these questions. So if I imagine my vertical line test with this graph, we are all good. So yes, it is a function. If you're ever asked why, you could just say that it passes the vertical line test. So we could say it passes the VLT. All right. Finding values and solving for values using our function notation along with a graph. So finding h of 2, so this is giving me x equals 2 and I want to find what's the output. So what I would do is go to x equals positive 2 and just look for my coordinate. So I have this coordinate x equals 2, y is positive 1. So this function notation, h of 2 wants the output of 1. So we can see our coordinate format of x equals 2, y equals 1. H of negative 4, in terms of what that equals, I would go to x equals negative 4, and then I want to find my output on the graph. So I have this coordinate down here, which is the coordinate x equals negative 4, and we would have an output of negative 5. So my answer there is going to be that output of negative 5, or my y value. So with those cases, they're giving you your x value and you just need to find the y coordinate that's being mapped on the graph. solving h of x equals -5. So this is a case where they're giving us y. And we could have multiple solutions in these cases. So we want to make a list of x values, and maybe sometimes there aren't any solutions. That can happen too. But I want to start listing x values that have y coordinates of -5. And what can help to do that is to visualize. So we're at y equals -5. It can help to visualize a horizontal line and then just looking for all intersection points. So we can see we have this intersection at 4, -5. We also have this intersection at 0, -5. And then that's all of our points. So we're going to have two values for x. We're going to have x equals -4 and x equals 0. So with that, we could have kind of two notations. In fact, one of the notations will exactly copy what we see up above there, which is the fact that if we plug in -4, we get out -5, but then we could see if we plug in 0, we could get -5 in a different spot. Okay, x equals +3. I'm going to do the same thing. So I'm going to go to +3 on the y-axis. And then I'm going to visualize this horizontal line and look for all the spots where we intersect. And it's just going to be this one spot at 3, 3. So with that, I want to grab the x coordinate is going to be our answer. So x equals +3. So we have this relationship that h of +3 is equal to +3. So that's how we can use our function notation with a graph. It comes to reading coordinates. Just need to keep straight which is your x value and which is your y value and which are they asking for.
So a little piece we're adding on here is how do we solve an inequality? So just to go over the things we've done so far. For B and C, we found values, and what we could even say is with those, we were evaluating our function, just using input, output. Given an input of x, finding that output of the y coordinate. And then with these, we changed to solving. So this was like solving an equation, keyword being solving, where we're given an output, and then with that, we can find all the possible inputs that work with that. Now with evaluating, with these scenarios, we should only have one value. And then when we're solving, as we saw, we could have more than one value. We could also have no values. So that would be a case of the answer does not exist. So we could have 0 solutions. We could have infinite solutions. Lots of possibilities when we're solving. With an inequality, and some of the notation we'll use here we'll talk about more in the next video where we go into domain and range. But let's go ahead and talk about how we would solve an inequality. So what this is asking is we want to know where is our function more than -1. And something to note is that this is talking about a y value of -1, just like how we talked about h of x is equal to a y value. This is h of x is more than a y value. So we want to find where is y more than -1. Now for the symbol here, we could see all sorts of possibilities. We could look for more than or equal to -1. We could look at less than or equal to, lots of possibilities there. But for this case, we're just going to look at more than -1. So I'm going to do similar to where we solved for an exact value. I'm going to draw this kind of horizontal line at -1. So let's go here and across. I can see I'm intersecting at a few spots here. So I'm intersecting here at -2, about 1.5, and then at 5. Now what's key here is that I want to know are the y values more than -1. So if we focus just on this y-axis, that means I'm looking for the cases where y is above -1. So where are we landing above that value of -1? Now we don't want to equal -1, so that piece means that at this -2, that's not going to give me any information there because we equal -1, but we never go above -1 there. So really what I want to focus on is here at about x equals 1/2. Let's call that a 1.5. What I can see is I hit -1, so we're equal there, so still not what we're looking for, but then we go above. So all of these values along the function, we are above -1, and it's perfect until we hit this value of 5. Right at 5, we're not going to be part of what we're looking for, meaning because we're equal to -1. But then just to the right of 5, we're above -1 again, and then our function ends right there at 6. So some key values here. What I want to express is basically an interval where we start at 1.5, we go to +5, we have a little break, and then we go from 5 to 6. So in terms of an inequality, what that would look like is for x, we want x to be from 1.5, we need x to be more than 1.5. And notice I'm not using equal there because we don't want to be equal to -1. And then we're going until we hit 5. And we also want to include from 5 to +6. So we end up with an interval of values for x where we're above -1. And it's all about trying to capture that if I have this region on my graph where I have all these y values that are above -1, anything that lands up here, I want to talk about where those x values are. Just like how we found x values for the solving for an inequality, same thing. It's just we're getting so many values that we need to express it with an inequality. Notation that we're going to use in the next video, just to give us a little glimpse, is we could talk about an interval 1.5 to 5, and then I would use parentheses to show I'm not including those endpoints, and use a U for union, and then we would go from 5 to 6, again using parentheses. And actually I'm glad I did this, because we actually can equal 6. That's where our function ends, and at 6 we're above -1, so I actually want to throw a little less than or equal to x equals 6. And then here for this notation, I would actually use a square bracket to show that we're including that endpoint. So a few different notations there. Either works for this, so you can express it either way, but it's all about looking for where those y values are above -1. Now, if this had been more than or equal to -1, then we would start including those endpoints there. So we would have like a single value at -2, and then here we would go all the way from 1.5 to +6. All of those would be more than or equal to -1. So changing it a little bit will change the solutions that go with it.